Good morning, class. My name is Benedict Sarti once more. We are continuing, or we are closing up, or trying to end this chapter on sizing conductors for PV systems. We went over the site, this sizing PV source socket over page 18. I'm just going to review 18. This is an assumption, and actually it's based on the NEC correction factors. Now, notice here they said the assumptions outdoor design temperature of 47 degrees Celsius. So 47 degrees is a very cold degree or less, covers all locations in the USA. No more than 9 current carrying conductors in conduit, 4 source socket maximum, conduit at least as 7-8 inches above roof, 1.25 1.25 irradiance factors included, terminal temperature limit verified, does not account for voltage drop. Now, if you look here, we have the the PV source socket. Now, let's say for 18.37 amps of a socket, you have the conduit, the conductor size of 10 AWG. So this is the wire size. When you look at this chart here, you notice that the greater the STC size or ratings, the lower the conductor. Over here, down below, we had 13.78 amps, and then we had 12 AWG. We have 11.48 amps. We have 14 AWG. A very important factor to look at. Now, this table shows Sarah's conductor size for PV source sockets, which have been calculated based on Sarah's maximum ISC ratings for model per 2017 NEC. There are several conductors that must be met in order to use conditions that must be met in order to use the wire sizing guidelines on the chart on this slide. When conductors are in conduit, it must be at least 7-8 above the roof surface. So we spoke about this. You cannot put a conduit on the actual roof surface. You have to make sure it's off the roof about 7-8 of an inch. So you have to be elevated off the roof for safety purpose, for a lot of factors. So you must make sure that your conductor or your conduit, the conduit is what we put our conductor in as a shield to protect the conductor from exposure to the UV light, a lot of things. So you need a conduit. All right, we spoke about that. The assumption built into this chapter make it a conservative guide in many situations, meaning wire may be oversized, but as long as the conductor listed above are met, it will result in safely sized conductors that meet all NEC requirements. Conductors can be larger than those specified above. For example, a model with an ISC of 8 or 6 amps could use a 10 AWG conductor, which may be needed to accommodate voltage drop requirement. However, they cannot be smaller than the minimum required without verification using more detailed calculations. Note that many installers just always use 10 AWG for PV source socket. In some cases, they could use a smaller conductor, but sticking with a single size means mistakes won't be made. And on residential scale system, the amount of money saved by going from a 10 AWG to a 12 AWG conductor when allowed is pretty small. On large scales, using the actual minimum wire size can result in significant saving in costs. They're saying here that some installer, all they do is that they don't change the size. They just stick with one size, and the entire installation is based on that size. The most common size they use would be a 10 AWG conductor. Sizing conductor for PV systems. Sizing inverter output socket conductors. With all NEC correction factors, without the NEC correction factors, with all the NEC correction factors, assumptions. No more than 3 current carrying conductors in conduit. 1 inverter output socket, maximum. 1.25 continuous Duty factors apply. Terminal temperature rely verify limits. Verify. Does not account for voltage drops. Does not account for voltage drops. Now, this is the size in the conductor for the inverter. They say inverter, look at the rating. Inverter rating, inverter, maximum output current per data sheet. Now, the data sheet will definitely tell you the maximum output current of that inverter. Let me see if I can go into my bank right here and see if I my data bank and see if I can find an inverter data sheet. Okay. Let me see if I can find a data sheet for an inverter. Serial parallel, mounting system, wiring. That's a data sheet. Okay, let's look at this power bridge, that power bridge inverter right here. It's reading. So we're about to look at the nameplate, the nameplate of this inverter here, the nameplate usually on the side or behind that inverter. So if you look at the nameplate of this inverter right here, the inverter, this power bridge 6,000 watts inverter is a modified sync wave unit. Now look here, the continuous power 6,000 watts. The peak low power rating 1200,000 watts. The input DC voltage rate range 10 to 15.5 volt. No load current drawn. I'm looking for this information. This is the information I'm looking for. The maximum output current. We are looking for the maximum output current of that inverter. Output voltage range. The output voltage range is 173 plus minus 10 degree, minus 10%. Maximum power efficiency 90 degree, maximum output temperature 65. Maximum output temperature 65. Low voltage alert. You can get this information on this here will not really be, it's not very helpful. I'm trying to find an inverter data sheet. This is a solar model, high quality solar model. Ooh, system type. I download the parallel series mounting. Q cells. For some reason, let me check my download. Let me go back to my download. My download record. I may find. I really want to look at a data sheet of an inverter, so we can go through it together. I have a lot of manuals on the model. Actually, I dropped the model. Actually, the model itself. But I want to have. I sure I downloaded some. I must have a download information about an inverter. I always, as you can see, these are all my download resources. My resource library for all of my downloaded materials that I use. I'm gonna search for it. Okay, look, I'll come out to it. INVERT. There's no photo phone with inverter on it. All right. So that's not helpful. All right, I'll come back to it. Now, on the data sheet, inverters come with a data sheet. On the data sheet of the inverter, there will be, they will tell you the maximum output current of the data sheet. They will tell you the maximum output current of that data sheet. The maximum output current of the data sheet will always be specified. You will always see the maximum output current. That will give you all the various readings of that inverter on the data sheet. The data sheet and the installation manual, the inverter comes with those are very important resources. You need those resources in order to do a very good installation. Some technicians, because of the continual, because of because they are familiar with the material, they don't always have to look at things because they donate a lot, so it becomes habituous for them. But as a beginner, it's important that you look for your MPPT and manual data sheet. Look for it's important that you do that. Very important. Very very important that you do that. Very important. No. I look for solar edge inverter data sheet. Solar edge right here. Let me go on the website. Excellent. So I found a resource that'll be very helpful. As you see my share screen right here, this is the solar edge inverter, single phase inverter. So they have different series of the inverter. But if you look at the output here, we have the maximum AC power output, the AC output voltage. These are the AC. This is the input. Maximum DC power, maximum input, maximum DC input voltage, current, maximum inverter efficiency, installation output, DC input. Come on, man. I need to find this match, man. Maximum output current per data sheet. This is not very helpful because this a greater inverter. This inverter is actually just meant for a system that work directly with the grill. So this is not very helpful. It's not very helpful. It's not helpful, but not very helpful. We get it now. But just note that you have to check on the data sheet to get these information. That's where you find your maximum output current per the data sheet. This table lists maximum conductor size based on maximum inverter output current. The maximum output current is given by the manufacturer. As long as the maximum output current is less than or equal to that shown in the left column, the conductor in the right column can be used. For example, a 3,300 watts inverter operating at 240 volt with a maximum inverter output current of 14 amps could use a 12 AWG conductor. Also consult the inverter installation manual for specific manufacturer information regarding conductor size. Again, voltage drop is not considered in this table and may result in a large conductor being required. Note, in some cases, the terminals in the inverter may accept a minimum size of conductor that is larger than the minimum conductor size needed based on amplicity. For example, a 10 AWG, the AWG stands for American gauge wires. So conductor may be sufficient, but the terminals in the inverter may not be rated for anything smaller than an 8 AWG, 8 AWG. In this case, the wire must be upsized to meet the terminal size requirements, even though, even though it is larger than what is needed to handle the socket current. This is different from the terminal temperature limitations discussed earlier. Socket must also be checked to ensure the terminals will not exceed the temperature readings, usually 75 degrees Celsius due to heat caused by higher current than will be allowed on a 90-degree wire. Note also that the method of using the continuous duty factor is chosen here, as it is the more conservative options than conditions of use deteriorating on a most but not allowed. Consistencies on the AC side, the NEC requires that either conductors of use factors or a continuous duty factor be applied, not both. Sizing conductor for PV systems. Example design diagram. The manufacturer supply model interconnections. We have PV array of what? How many model we have in the series? 1, 2, 3, 4, or 1. Okay, let's just say 2, 4, 6, 8, 10. No. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is 10 PV model in a series. You notice the connections, series connection, parallel running to your junction box, series connections, parallel running to your junction box. On the junction box, you have you have the socket coming down to our disconnect. We have a socket from our disconnect to our inverter. From our inverter, we have the conductor for inverter output. This is the conductor right here running to your AC disconnect. Select conductor for PV source socket. All right. Now this schematic will be used for the following wire sizing example. Note that the inter model connections wire model lead do not have to be sized as they are supplied with the models and size at the factory. The grounding conductors are not shown in order to simplify the diagram. In this system, the PV source socket are all individually run to the inverter rather than to the combiner box. For example, for this reason, there are not any PV output socket except internally in the inverter, and there are essentially two home runs, one for each PV source socket. The junction box used to transition from the outdoor RITs USE 2 or PV wire conductor to less expensive wires such as the THWN2. Remember when we're discussing wires, we talk about the different types of wires and the ratings and why are they used, which wire is appropriate for outdoor wiring and which wire cannot handle the UV lights. Which wire is good or is used for underground runs. So it's important that you know your wires. The inverter output socket runs from the inverter to the DC disconnect and then to the main AC service panel. This is very explanatory. You know, right here we had 20 PV model in series. We had 10 model in the first series out here, and we have another 10 model in our second series. we have our socket runs to our junction blocks. Notice that you are not running each model is now running a socket to the junction box. We pair them in series and then we run the parallel connections to our junction box. We discussed this when we're talking about a parallel and series and parallel connections. That is very, very juicy, man. I like it. Sizing conductor for PV systems. Select PV source socket conductor. Now look at here, the model STC ratings, the pseudo word SWG290. This is the socket conductor sizes here. This is the model readings. The model reading the VOC, the VMP, the ISC, the IMP, and the W. Now let's look at a model. I'm going to look at a PV model. I want to see if I have a data sheet for. I have a lot of information on the model. I have a lot of information on models. I may not be found it difficult to find a manual. Oh, that's a manual. I want a data sheet. It's a manual, but let me see. There's an installation manual. Excellent. I found a data sheet. This is very, very, very helpful. Now let's proceed. Let's move forward. Here is a data sheet right here of a PV model. The PV model we're talking about here is called the Q. This is a Q cell PV model. The models we have here, and this is a data sheet, and here is the electrical characteristics of this PV model. When we look at the power class, you have the 380 watts, the 385 watts, we have 390 watts, we have 395 watts. Those are the power class of the PV model. What they call in Africa or Liberia, the solar panel. The technical names name is models, PV, which stand for photovoltaic. So the PV model. Now the power at the MPPT we have here, you notice that it will move forward backward to our material, RSC. Let's look for the ISC. ISC, short circuit current. They're giving you the short circuit current for this model. And you know that we discussed that you have to include the 1.25 to find your radiance. I mean, we talk about the 1.25, then we talk about adding another 1.25 in order to for proper sizing of your PV sockets. We spoke about that in previous chapter. Just want to refresh your mind. We have a 9.97 amps, a solar wall SW290. So this is just this model. They're talking about this model. They're just using, this is the same information here. So for that 290 watts PV model, this is the own ratings. Now this is the PV source socket current. They're saying that the recommended conductor for this model 290 would be 14 AWG, and you have 11.4A. If you look at right here, the source socket is 9.7, 9.97. So I'm going to do this for you. Let me see if I can work that math right now. I'm going to go behind it. 9.97 times 1.25, okay, times 1.25, all right, 13.5. So we have 13.5, I mean 12.5 times 1.25 1.25 12.5. Okay, 12.5. All right. So if you notice right here, the class, they added the short socket here. Let me go back. I'm going to run back so you can understand this. Sometimes I like to refresh our minds. The maximum current. The maximum PV source socket current, ISC times 1.25 to find your irradiant factors. You have to find the irradiant factor. So when you notice that on that chart, they have 9.97, that is the ISC. But what they did was that they did the calculation already. That's why they were able to tell you they already did factor in the 1.25 on the ISC to find the irradiance. So they did find the irradiance. They did that to find the irradiance as well. Number of socket parallel, so the ISC times 1.25. They did that already. So then they did the continuous duty, which is the ISC times the 1.25 times 1.25. So they did all of that. That is why you see at the end, they're telling you here, what page was that? Now they're saying here if you notice 9.97 amps. That is the ISC reading of this model. But when you look down here, the STC ISC greater or less than 13.78 amps, the recommended this. At 11.48 amps, the recommended 14 AWG. So just take into consideration, they already did factor in the irradiance. That is why they have the ISC rating, the PV source socket ISC rating, the STC rating right here of 11.48. You have to. You cannot just size your conductor, your socket conductor based on the minimum, based on this given, based on the open current voltage, based on the short socket voltage, which is like for example, you had 10.5. For this model, you have 9.97. You can't just size based on this. You must factor in your 1.25 for your irradiance. Is that clear? Very important. They did that already. The model in this example is a solar wall XW290 model, which has a short socket current of 9.97 amps. Remember, all the assumptions previously outlined must be met to use this table. Since the ISC of this model is less than 11.48 amps, the minimum wire size required by the NEC for the PV source socket conductors is 14 AWG, and all 4 of the current carrying conductor from the 2 PV source socket can be run in the same conduit. Right? Let's look at right here. We move forward. Sizing conductor for PV system. DC voltage drop. We have your DC voltage drop. VMP model times model in series equals array, which is array VPM. 13.4 volt times 10 model in series, equals 114 volt. The AC or DC voltage drop calculator. So there is a calculator here called the AC or DC voltage drop calculator that maybe we will be talking about. The distance of conductor size, the single or three phase. Is a single or three phase. The conductor type, the installation, the voltage, the maximum voltage drop, the length of cable run, the current, all of those information, you need them to be able to do your DC voltage drop calculation. They have a calculator for that. VMP. Let me look at my model right here. Is that VMP? VMP, 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 VMP right here. All right. Let's just put a P there. So with 39.71, here the VMP vote is 31.48 volt. Those are arms. I'm looking for the vote. We'll use this one. The VMP vote. 37.48 for a 380 watts Q cells panel. 37.73, 385, 38.04, 390. So on your data sheet, this I'm referencing this data sheet because this is what an actual data sheet of a PV model look like. You will have a data sheet for every model you have to install. If you don't come with it, you have to research the data sheet from the web manufacturer website, and it will give you all of these readings. So we have the vote right here, 37.4. If you notice here, they give you they give you an example of the VMP 31.4 volt. Now that 31.4 volt, you're gonna multiply it by the amount of array, the amount of model in an array. When we discussed what an array is a group of model. When you put a group of panels together, it becomes an array. So the given array here is 10 array. Given model here is 10. So we combine 10 models in a single given array. So that says that each model VMP is 31.4 volt. We take the 31.8 volt, we multiply it by the amount of model in an array, which will be 10 model. So I'm going to go use my electrical assistant here. All right. So we have my calculation assistance here. 31.4 times 10 model, 114 volt. When we did parallel and series calculations, because these model are in series, the arm remain the same, the voltage increases. So that's what they're saying here is that we have 10 model here. The arm remain the same. The arm is not changing here. It is the voltage that increasing. So we have what? We had 314 volt. Very important. And that is why the PV model data sheet was, as most often tells you, it should tell you what is the maximum of model you can put together in a series. The maximum. Let me see if I can find that information. Very relevant information. The maximum system voltage, 1,500. That's a safety class 2. So that's the maximum, 1,500. The maximum system voltage is 1,500. So if you're combining them into series, the voltage will be adding up. When you reach 1,500, you stop. You can't go to 1,500 and 10. You can't do that. Then you'll have a problem. That's why we have to know when it comes to PV. The whole thing about PV modeling or PV installations is calculations. It's physics. It's a little bit of math, but it's calculation. You have to know your calculation too. Your calculation is very important. You have to know your calculations. Calculation is very important, and you have to be on point with your calculations. It's very important because this PV model, that's why people don't understand. We have monochroming and polychroming. They have the polychroming in Liberia. Those PV model rating guarantee for even 10 years the max. But when you get a monochroming, you're guaranteed for 25 years or more of reliable electricity from your model. That is why calculations is of very importance. So they just said to you, tell you right here, 1,500. Now let's go do some reading. There's a calculator, AC to DC voltage drop calculator. I show that you have, sometimes you have apps you can download. I just bought an app from the Apple Store on my phone, and it tells you exactly how to do a lot of calculations, needs analysis, what connections to use. It tells you right there. It tells you that. The only thing I don't like about it, the PV models they have in there, the maximum is 330-volt conductor phase utilizing utilizing a 14 AWG copper conductor will limit the voltage drop to 1.19% or less when supplying a 9.33 amps for 75 feet on a 314-volt system. All right, let's read small. This slide shows how to calculate voltage drop using an online calculator. This tool available at thewinsum.com. North Arizona Wind and Sun can calculate both wire size and allowable wire distances. There are many other calculators. There are many other calculators are available on. There are many other calculators are available online. There's a grammatical error in here. There are many calculators available online. Available online. Another popular choice is softwire.com. But when using an online calculator, always double check the accuracies. Voltage drop is calculated using the maximum power voltage and current, the VPM, the IMP, respectively. The specification for the solar wire SWG298 models shows the VPM is 31.4 volt times the amount of model, which is 10 models in series, equals 314 volt. The IMP, which is 9.33, is so socket run directly to inverter. You notice that the IMP, 9.33, this is amps, didn't change, run directly to the inverter. This distant one-way length also need to be entered, which in this example is 75 feet. The total calculated, the tools calculates that a 14 AWG conductor will have a voltage drop of 1.19%, well within the acceptable range of this of less than 2%. Now, some of the biggest problem with PV module installation in Liberia and other places in Africa, I pray God for the time that when I build my team, my technicians, we will be able to not just do job in Liberia. I'm not limiting this dream. My technicians should be able to travel to Ghana and compete, should be able to travel to Nigeria and compete, should be able to travel anywhere on the continent or beyond and compete because this is international standards. All of these, I'm telling you, this is standardized training. These are training that you can use, or my technicians under my voice should be able to use. I'm humble in saying this. Very important. Pay keen attention. Remember, the combination of sizing to meet ampacity and voltage drop requirements means that if there is a difference in the conductor from either method, the larger of the two sides must be used. For example, if a PV source socket was required to use 10 AWG to meet the NEC ampacity requirement, but due to the length of the socket, the voltage drop calculations result in 8 AWG to stay around 2% voltage drop. Then the 8 AWG will be selected to satisfy both criteria. Very explanatory. I have to end this chapter. Now let's look at the choice inverter output socket conductor. We're just talking about your model. Now we're talking about the inverters. The inverter data sheet or the inverter nameplate. On the inverter, you will find something called the maximum inverter AC output. 24 amps AWG. This is the maximum output. It tells you all of these readings on the inverter nameplate. The maximum continuous output power is 5,000 watts. The inverter in this sample systems is an SMA Sunning Boy 5.0. It is rated at 5,000 watts maximum continuous power and operate at 240 volt. The maximum output current listed by the SMA is 24 amps. So the smallest conductor that can be used is 10 AWG. Why? I want to explain. Now this is an AC volt drop. The input parameters. The conductor size is 10. The voltage is 240 volt. The maximum voltage drop is 1%. Typically 3% or less in the recommended is the recommended level of efficiency operation of equipment. Current at the end of the cable runs at 24 amps. Result, a maximum distance of 47.649 feet will limit the voltage drop to 1% or less. So they just tell you when you maximum, when you're doing your runs, the maximum distance of 47.8 to 47.6, I would just round it up to 40, that would be 48 feet will limit your voltage drop. So if you're doing your runs, your wire, your conductor runs, remember they just tell you by using the calculator here that once you reach this amount of feet, you're going to have some voltage drop of 1%. So with a number 10 copper conductor delivering a 24.0 amp on a 240 volt system. So we would use this calculator when we start practicalizing or in the next section of our class when everybody is in class. The voltage drop must then be calculated for the AC size of the system. This calculator is from the softwire.com. Entering the conductor size 10 AWG, the socket current 24 amps, and the desired maximum voltage drop limit 1% shows that a socket length of 47.65 feet will limit the voltage drop to 1% or less as desired. In this case, the same 10 AWG conductor certifies both the NEC and the voltage drop requirement, but this is not always the case. If the actual distance of the socket was longer, voltage drop would be greater, and a larger conductor will have to be used to keep voltage drop at or below 1%. Note that even if a smaller wire will meet voltage drop requirement, the wire size cannot even be smaller than the calculated NEC required size. You cannot use a smaller wire than the size recommended. The NEC recommended size, for that inverter, for that conductor or the socket or the conductor, you must always remember that. Now let me see here if I have some. I was looking for my inverter, I can't find it. But I just want to see if they talk anything about runs on the data sheet. They spoke anything about size of a conductor. Maybe let me see if it's on the data sheet of this conductor, if there's anything mentioned about the size of wires. The cable. Oh, this is the model, the cable here. I don't see anything. Maybe it's it will be on the manual. Maybe the installation manual will have something about the wiring. But there is always recommended. It always tells you what kind of wire, what appropriate to do. to use. It's always there. The information available, use them. Don't depend on you. Don't depend on your expertise. Many people, because they do jobs and they say, "Oh, I've been doing it for 10 years. I've been doing it for this year." When it comes to anything that has to do with current, you always have in mind that you are a continual learner. You are a student at all time, because you are the lives of people are at risk based on what job you do. If you do the wrong job, use the wrong wiring, don't follow the NEC requirement, the NEC guidelines, you do sloppy jobs, could cause fire, could burn somebody's home. So it's important that you follow these guidelines. Wire sizing summary. Okay, let's summarize. The minimum wire size, the NEC for PV source socket is 14 AWG. For inverter output is 10 AWG. For voltage drop, we have 14 AWG at 1.19%, 10 AWG at 0.78%, 79%. The required size is 14 AWG. The required size is 10 AWG. To summarize this wire sizing example, two PV source socket will be wired using a 14 AWG conductor, which meet both the NEC ampacity requirement and voltage drop requirement. The inverter output socket will be wired using 10 AWG conductor, which also meets both the NEC ampacity requirements and voltage drop requirements. In many cases, smaller with standardized on a minimum of 12 or 10 AWG conductor for PV source socket. For durability reasons, each of the installations, by keeping it the same, and possible cost saving of always buying the same conductor in bulk. We'll go over this in the class, and you guys will have to do that exercise. Let me summarize this. Let me include this. So that is the end of that sections. Very important. All right, stay tuned. We'll be moving on to our another chapter, but this is the conclusion of this chapter. When we all get into class, we will discuss in detail. We will go through the exercise material together.